So, covalent bonding. Now here, again, electrostatic force of attraction. But we're looking, in this particular case, between two atoms. So the force of attraction is not in all directions, it's only one direction. So two nuclei will have a shared pair of electrons between them. And it's the attraction of the two nuclei for this shared pair of electrons that produces the covalent bond. So again, I'm generalizing very much. Covalent bonds can be formed when a non-metal reacts with a non-metal. So it's generally two non-metals, but there are exceptions to these rules always. Lots of exceptions, as we shall see later. So again, a generalization to say that they share electrons to obtain full outer shells. It's very much a simplistic model here, as we shall see very, very soon. So we've got to be very careful with this. Now, you can form different sorts of covalent bonds. You can form single covalent bonds where two electrons are shared, where four electrons are shared. You can form a double bond, and you can use 6 electrons to form a triple covalent bond. Now this table contains an awful lot of information, so I'm going to take it fairly carefully and steadily. So let's start with period 1 and hydrogen. Now hydrogen has 1 electron in its outermost shell. By sharing 1 electron, it can gain an extra electron to give it a total of 2. And that gives it noble gas electron configuration. So hydrogen will form 1 covalent bond. Helium, a noble gas, already has noble gas electron configuration, so therefore will not form any covalent bonds. Same for neon just below it. Now we'll work backwards to group 7, fluorine. Now fluorine has 7 electrons in its outermost shell. It needs 1 more to gain a noble gas electron configuration. So therefore it can share 1 electron to form that 1 covalent bond. Oxygen, with 6 electrons in its outermost shell, needs to share 2 electrons to get a total of 8, and therefore it will form 2 covalent bonds. Nitrogen in group 5, 5 electrons in its outermost shell, needs 3 more to attain noble gas electron configuration, so by sharing 3 electrons we'll gain an extra 3 to give a total of 8 electrons, noble gas electron configuration, isoelectronic with neon, 3 covalent bonds. Carbon, group 4, needs to gain 4, so sharing all 4 electrons, it will become isoelectronic with neon, with 8 electrons in its outermost shell. But this is where our simple model breaks down, because when we get to boron, now boron has 3 electrons in its outermost shell. If it uses all 3 electrons in covalent bonding, forming 3 covalent bonds, it will produce 6 electrons in its outermost shell. Not noble gas electron configuration. Same for beryllium. And beryllium, of course, you can think of as a metal. We've already said that covalent bonds occur between non-metals and non-metals. Here we've got an exception to the rule. It gets a bit confusing. And again, we'll only share 2 electrons to form 2 covalent bonds, 4 electrons in its outermost shell. So there are always exceptions to the very simple rules. And it gets more complicated when we get down to period 3, of course, because with period 3, the third shell of electrons, the third energy level, not only has S subshells and P subshells, but it also has D subshells. So potentially there's room for 18 electrons around a central atom to fill that energy level. Now that means that whilst argon, noble gas electron configuration, generally does not form covalent bonds, chlorine could form one covalent bond, that would give it 8 electrons, making it isoelectronic with argon. But potentially it could use those D subshells to produce 3 or 5 covalent bonds. Potentially there's room for 7, but trying to get 7 atoms around a chlorine is potentially quite difficult. Sulfur, similar to oxygen, gaining 2 electrons to form 2 covalent bonds by sharing 2 of its electrons, isoelectronic with argon, but it can also form 4 or 6. Phosphorus, sharing 3 electrons to get to noble gas electron configuration argon, or potentially 5 electrons. Now that means you will have a total of 10 electrons surrounding that central phosphorus, not noble gas electron configuration, not a full shell of electrons. Silicon goes back to 4 noble gas electron configuration. That's as far as it goes. Aluminium, very similar to boron, sharing all 3 electrons to form covalent bonds, but it's not noble gas configuration. You will also notice that aluminium forms ionic compounds, which is what you would expect with a metal. But again, covalent bonding is not expected with our very simplistic model of non-metal plus non-metal.